Today, we're talking about relative motion. So, what if your cousin runs across the street? You need to understand that, right? That's an attempt at humor, relative motion. Actually, what I mean by that is this exciting screen share. Suppose we have, and again, we're on page 78, like I mentioned as we were getting ready. 78. Suppose you have two objects, A and B. Both of them are moving relative to the Earth. That's what I mean by relative here. Relative to what? The idea here is if A and B are moving relative to the Earth, you could view this as, let's say you were person B, okay? And person A is running slightly upwards here towards you, and maybe this is a top view. What we see is from B, from the perspective of B, from B's location, A is moving towards B much more rapidly than it is moving relative to the Earth. So again, this arrow, oops, sorry. Let me get that color. This arrow right here is talking about the velocity of A relative to the Earth. When you factor in the fact that B is also moving and account for that motion in a way we're going to describe mathematically in a minute, we get this different velocity vector here. And this is the velocity of A relative to B. At first glance, this may seem totally worthless to you, but I'll mention a couple of applications. Obviously, if an inbound ICBM is headed towards your Vandenberg Air Force Base, which is right nearby, it would be nice to know the velocity relative to your missile so you know where to aim the missile to shoot down the other missile. I was mentioning to the other class when I was a kid, right? There was Iraq War One, and in that case, the Patriot missile defense system was used. And so there's one application of if you want to hit an inbound missile, you need to know the velocity of your missile relative to the other missile. Maybe a simpler version might be imagine these are two airplanes flying. Well, the airplanes that are up in the air, they worry about the velocity of other planes relative to them. And they also worry about their velocities relative to the wind. And they also worry about their velocities relative to the ground. So you can imagine there's all kinds of cases where this might matter. If you are a mechanical engineer and you're working on a device that has multiple moving parts, this might be important. So that is a few of the reasons why this might be something you should care about. Another reason is, let's face it, for a lot of you, you might not be doing that. But I do want to point out that this gives us one more option or one more way to practice vectors. And we want to make sure we understand vectors in this class very well and the math involved with them. So periodically, we're going to keep touching on vectors. Now, everything that we've done so far has pretty much involved vectors, except for the first chapter, which was units and such. But every other chapter, I don't know if you've noticed this, I try to get something with a lot of vectors in it. Now, I do want to point out something very special here. And let me maybe put it here. Notice this little equation. If you switch the order of the subscripts, that introduces a minus sign. For all the other problems in this chapter, we've been using V2 final in the X or VX final for number 2. And we didn't really care about the order of the subscripts. When we are talking about relative velocity, things matter. Look at what these sentences mean right here for those two symbols. Okay. The velocity of B relative to the Earth is different than the velocity of Earth relative to B. So just to be clear here, so it's all in one spot, order of subscripts matters. So put that somewhere in your notes. So the order matters now. And we see in particular, it's a lot like cross products. If you flip the order of a cross product, you get a minus sign. If you flip the order of the subscripts in a relative velocity problem, we're going to flip the sign of the vector. And maybe I could show you this here. If I get some of this stuff out of here. I just want to show you this velocity vector B. Notice this one right here, and let me use a bigger, right? This one right here is going that way. So VBE is going mainly to the left and a little bit down. Notice VEB, this vector right here, VEB is going a little bit upwards and to the right. So notice it's exactly opposite or negative of the other vector. Compare those two vectors. That's what I'm saying here. Now,
so why would you go through that trouble? Why couldn't you just minus VBE off of VAE? But if I have VAE minus
you could
VBE, right? It's the same thing.
You could. And so I'll tell you why right now. This is why I do it. I have this formula right here memorized in a certain way. And so I need to know that other piece of information. And I want to point out, look at this formula right here that I'm drawing the orange arrows at. The idea here is, let's say this is just how I have it memorized. It's not like there aren't other ways, as Esteban was pointing out. For me, this makes it easy to memorize. If I want the velocity of A relative to B, notice the letter E. Let me do this here in a different color. Notice the vector, the symbol E is the in-between vector. You're going to hear me say this over and over again. It's like the letter E gets squeezed out of the equation. And so the idea is I remember it this way because I remember that the letter E should be squeezed out. All right. And that's just, and then, so if I want to do calculations, I also need this piece of information because it's just to help me use these equations that I've memorized. So is that good, Esteban? It's for no other reason than it's easier for me to remember that.
Yeah, I see your logic.
Yeah. And then the other thing is this was, good question. Now, I'm going to try, I don't know if this will make sense to you. I don't know how well the simulations work. But so what I did here, let me clear all these drawings. I wrote up a little code during office hours for somebody. Now, this may not make a lot of sense, but I'm just going to show you the basics of the code. This is supposed to be the I hat. This is the J hat. And this is the K hat portions of these vectors, right? So I, J, K, right? And the idea is the equations, we could do this with full three-dimensional vectors if we learn to do this right. This is the line that I was just telling you about, and this is the line that I have memorized. But notice, here's a quick case where I can use that memorized line to save myself some effort. If I know the velocity of A relative to B, and I already did the math for it, it's easy for me to figure out the velocity of B relative to A by just flipping it. Now, in the code, you don't see the vectors, but, I guess it's drawn a little bit differently. Instead of drawing an arrow over it, notice I put VEC for vector. All right. So let me clear that out for a second. Now, what have I done in this code? What I've done is I've actually, this is kind of cheesy, but if I want to do the motion relative to A, I'm going to uncomment this section of code. If I want to do the motion of B, I do this. And then right now, this is set up just to look at everything relative to the Earth. So you don't need to understand all that, but let's just take a look at it. So there's the idea. There are two balls moving. Maybe there are two cars driving away from an intersection or two planes leaving an airport. All right. So let's go back into here. And the idea is, just a second, I'm going to comment this out. Let's say we want to understand the motion relative to A. So now I'm going to look at this one. The idea is if I'm looking at motion relative to A, I pretend A isn't moving. And then I look at the velocity of B relative to A and the Earth relative to A. Now the Earth in this case is going to be these two lines that were my coordinate system. So let's go ahead and take a look at this. Let's run it this way. So again, we're looking at the motion relative to A. From A's perspective, A is sitting still, and you see all this stuff moving away. right? That little white dot was the original origin. So that's all that was, if you're curious. So what if I want to understand the motion relative to B? Let's just get a feel for this. And we'll just see the motion relative to B now. So in this case, the blue ball should be sitting still, right? And we see everything moving relative to the blue. So the idea is we want you to be able to understand this. And obviously, writing this in a computer code makes it very easy. But if you don't understand a paper and pencil, how are you really going to code this thing? So, yeah, that's, I don't know. That's our goal, is to try and understand how motion looks from different people's perspectives, right? So from the blue ball's perspective relative to B, how do things look? From the red ball's perspective, how do things look? Let's start very simple, okay? Let's start simple. And by doing that, let's go back to the screen share and tell you, rather than try and do the hardest problem in the world, let's start with the easiest. And let me show you that one. So I'm going to write up all this stuff on the board and work through it with you. These definitions and equations are meaningless without practice. While they're going to seem simple for the first 1, 2, or 3, you would be surprised. Almost every year, students miss relative velocity questions, especially in 161 when I make them difficult. Okay, so let's start as simple as possible and do it with the full notation so you get used to it, even if it seems easy. You probably can read this right now and tell me the answer. Let's just kind of look through it really quick. You've got student A walking due east. We've got student B is hustling at 3 meters per second. If you want to convert these to miles per hour, remember you basically double them, maybe double and add 10%. So 2 meters per second is about 4 miles an hour. You could imagine that's a brisk walking pace. 3 meters per second is about 6, 7 miles per hour. So that's like you're jogging. All right. So the idea here is, if this one's going this way at 2 and this one's going this way at 3, if I put A here sitting still, the answer should be this one moving that way at 5. Hopefully that makes sense to you, right? Basically, they should be separating faster than 2 or 3. So, now where it's going to get tricky is when things are moving at right angles or at goofy, east, west, south stuff. So just be patient. Let's learn the notation. All right, so let's start this one out. I'm going to draw it on the board really quick, and then I'll stop sharing screen. So 426 is where we're starting. Remember, at any time, you could talk to Memo. I'm going to use blue for B, red for A for right now. In one of the solutions, I accidentally switched the colors, but other than that, that's pretty close. All right, and so simple picture. Let's get used to writing down the words correctly. This is the velocity of B relative to Earth. It would be negative 3.00 meters per second I hat, because it's going to the left. The velocity of A relative to the Earth is positive 2.00 meters per second I hat. So this is going in the positive I hat, that's going in the negative I hat. So now if I try to use my theorem here, velocity of B relative to A, I think that's what we were asked for. Determine the velocity of B relative to A. So it's always first object relative to second object. And again, this is how I remember it. I just say, well, I know I need a B on the outside here, and I need an A on the outside here. And this helps me remember it because I see E is in the middle And this is just how I have it memorized. I know if E is in the middle on this side, that is the variable that gets squeezed out on the other side. That's nobody else says that, but that's just how I remember it. If that helps you, great. If it doesn't, you don't have to say it that way. Now I can see right here, I have AE, but the equation I have memorized calls for EA. So now, just because it's easy for me to memorize this, I'm like, oh, well, all I have to do is switch this. And if I switched it, I introduce a minus sign. So I'm going to rewrite VBA is equal to VBE minus VAE. If I switch the subscripts, I introduce a minus sign. So now we see we're basically doing vector subtraction instead of addition in this problem. Big deal. So what Esteban was saying earlier is, can't I just write this down if I see it? Sure. If you see that, great. This is just easier for me to memorize. Next, let's plug in the numbers. Now I could tell there's going to be a meters per second on each term here. So maybe I'll just put that out at the end right now. Meters per second. And then it looks like I'm going to get a -3 in the I hat. Remember, I already had the meters per second there. And then minus 2.00 in the I hat. All right. Sorry about that. So now in this case, at this point, it's just -5 in the I hat, which is what we expected. So if I could, I'll just squeeze that in there. I know that seems like overkill. It really is. But this gives us an idea. All right. So far, so good? All other problems are pretty similar to this mathematically. What may change now is, at some point, figuring out the I hat and J hat parts is going to be trickier. So let's go ahead and do our next one. Let's not overthink. Let's just build this up naturally, okay? So let's try 4.27 now. Okay. Oh, I didn't do the picture. Let me do that really quick. So check this out. We said A was moving at 2. B was moving at -3. Sorry, I'm just doing part B of the previous question before we go on. And then we're supposed to look at this from B's perspective, right? So from B's perspective, this is what it looks like. B sits still right in the middle of the screen. Oh, wait, oh, shoot, I just did it wrong, didn't I? That is the perspective of B. That's the velocity of A relative to B. I misspoke. We're supposed to be getting the motion relative to A, aren't we, in this problem? So my apologies. So let's do this right. So now A should be sitting still. Notice A's velocity vector is going to be 0. Sorry. So from A's perspective, there goes B off to the left. All right. Cool. Let's get out of that. And we'll go to the next one, which is, I lost it already. So now let's try 4.27. Okay. Is the simulation helping or not? Just tell me, be honest. If it's wasting your time, I won't keep doing it.
It helps visualize.
Does it actually kind of play, or is it too laggy? Is it good enough? Go ahead.
I was going to say that I get kind of confused with the simulation as whose perspective we're seeing. So
the perspective is whoever's right in the center.
Right.
Yep.
Right.
Okay.
Yeah, but like how right now when you made the mistake, I could swear like I understood what you were saying, and then you did that mistake, and I was like, see, that's I
Yeah,
can't really, I
yeah.
don't really understand that simulation.
Yeah, so by the time we finish, it'll be good. So this helps me right here, this statement. Imagine a drone is hovering above the student, A or B. So imagine if you had a drone that was filming people, spying on people, right? And so if you had that, if the drone is directly above A is always going to be right in the middle of the picture. And then B would be moving out rapidly. If the drone is hovering above B would be centered in the picture and A would be moving out. So that's kind of what I try to imagine. If we're figured out relative to A, imagine the drone is locked on person A, seeing anybody who comes in contact with A. All right. So let's try 427 now. Should be pretty similar, right? I'm going to leave off the sig figs just because I'm lazy right now. So now we got this. So again, in this particular case, the only difference here, well, there's no difference for A. Again, I'm leaving off sig figs for clarity, or just for brevity, I should say. We get a J hat on this one now, right? So in this case, if I try to get the relative velocity, oops, I want the velocity of B relative to A, that is going to be VBE plus VEA. Now I have my squeeze out. E gets squeezed out. Now I see, oh, now I need to change this to VAE. If I'm going to figure out, if I'm going to use this, I need to do a subtraction there. And let's just see how this differs, okay? And again, I'm trying to layer up the complexity. So you're probably thinking this is not that much different. There's one thing different at the I know there's going to be meters per second on everything, so I'll factor that out. BE is -3 in the J hat. This is -2 minus a +2 in the I hat, right? Normally we switch the order of these now. So normally you would say the I hat term first, -2 in the I hat, -3 in the J hat, meters per second. And if we want to get the magnitude, how would I get the speed? How would I get the magnitude of this?
Pythagorean theorem.
Yep.
Square root of 2 2
Sure,
square plus 3 square.
What would I do before doing that? What is a good habit for every physics student when you get a vector and you want to understand it? What should you do before you do the Pythagorean theorem?
Draw it.
Draw it. Excellent. And so Esteban probably was already there. He was drawing it in his mind. So notice this one's going 2 to the left and 3 down. Sorry, that's a little, I got to go downwards here. So now this gives us a feeling for this. In this case, we've got a side 2 that's negative because of the arrowhead. We've got a side 3 that's negative because of the arrowhead. And now I can see this is going to be 2 squared plus 3 squared. What is that? I'm going to cheat and go to the solution, okay? Because I happen to have it worked out. So it looks like when you do the Pythagorean theorem, you get 3.61. All right. And notice this angle in here is 56.3. And then maybe I'll put this down here a little bit just so I have some room. And I'm going to go back to here. Sorry, just a second. So the idea is this length is 3.61, 2 squared plus 3 squared, square root. Gives me that. The angle, how do you get the angle?
Tangent, inverse tangent
Of
2/3 or three twos.
So this angle will be tangent inverse of opposite over. Yes. So it's, and that's what I was looking for. And he got it. So you have to, that's the thing that you do want to watch out for. And now you know why we actually took the time to go through this. You got to remember that to get the magnitude, you got to do the Pythagorean theorem. And here you got to do inverse tangent, and make sure you remember to get the opposite over adjacent if you're getting the angle. Furthermore, there's one additional thing I want you to watch out for. We're taking a class where we have online quizzes, right? So in Canvas, you have to enter your angles between negative 180 and positive 180. So if this is 0 degrees in a Canvas quiz, this angle would be, I'm going to figure that out. (180) minus that number. 180 minus 56.3 is 123.7. And so in a Canvas quiz, you'd have to enter this as a negative number because it's below the x-axis. So I believe on all your Canvas quizzes, if I ask for an angle, I say, please enter a number between positive 180 and negative 180. Okay. So far, so good on that. Any questions on that? Go for it.
No, sorry, no questions.
All right, so let's go take a look and see how this simulation differs, right? And so far, this probably seems pretty easy. Don't worry, it's going to get hard quickly. All right, we're trying to learn the basics at an easy way, and now I'll just start punishing you severely. So in this case, we had, this one was -3 in the j hat. So now when I run this one, let's see, we're going to look at the motion relative to A. Okay, so which object should be sitting still if we're looking at the motion relative to A? A is sitting still, and we're going to look at the velocity of B relative to A. Now the Earth relative to A, that's the coordinate system, right? So think of the coordinate system in this problem as the Earth. A should be moving to the right, which means the coordinate system should be moving opposite direction, right? If A is moving to the right relative to the Earth, the opposite is true for the Earth relative to A. So let's run this and take a look at it. So notice the Earth's moving there, and notice the ball is actually moving straight down. I don't know if you can see that. And so what I could do here is I set the initial positions. I could actually set them both at the origin just to make this a little bit more clear. And maybe I'll set this just slightly. So I'm going to put them almost exactly on the origin to start so you can see it better. And notice B is moving basically straight down there, and A is moving to the right. But as A sits in the center of the screen, we notice that B is essentially moving off at this crazy angle. So from A's perspective, B is moving that way. That's the velocity of B relative to A.
And that's that 56-degree angle we saw
That's
too.
that 56. Notice this is moving off this way. That's the velocity of the Earth relative to A. And then over here, the velocity of A relative to itself, well, it's not going outside of itself. Unless it's having an out-of-body experience, it's moving nowhere. A is not going anywhere relative to itself. I don't know about you. Sometimes I really annoy myself. I wish I could go somewhere other than where I am sometimes, but it just doesn't work. You're trapped in your body whether you like it or not. Okay, so that was what that was supposed to be all about. All right. And then maybe just to get a feeling for it, remember, let's go like this. Let's comment this out for a second and open up this one. So this is what the motion looks like relative to the Earth. So again, think, if this is relative to the Earth, the coordinate system shouldn't be moving, and these are now velocities relative to the Earth. Let's look at it. And that's what's happening here. So notice the Earth's coordinate system isn't changing. A is moving to the right, et cetera, et cetera, et cetera. Okay, B was moving down. All right, so let's get back out of there. Where were we here? Let's see if we've killed that problem off. So hopefully this is giving you an idea. So from A's perspective here, oh, whoops, I'm on the white. Sorry. From A's perspective, that just means relative to A. Okay. All right. Now let's see how you do with this problem. I'm going to let you set it up. Now you see you have to draw the pictures yourself, and this is starting to get more like a real exam question. Now that we kind of got the mechanics of the plus minus signs and the subscripts, let's see how you do setting this one up. I'm going to set it up as well, but hide my whiteboard, and then we'll look at each other's work in another minute. So take a minute to set this up. 4.28.
Is it possible to calculate this in polar form, or do we have to go to rectangular form?
Well, what do you think? What's your gut tell you?
Well, so far right now we've only done it in rectangular form, so I'm guessing that's the only way to do it.
Yeah, let me put it this way. It's easier to convert to Cartesian, then do all the calculations in Cartesian, and finally unconvert or switch it back to polar. That's the standard way we did vector addition in chapter 3. Remember that?
Yes.
And so there are tricks for two vectors to figure it out without that in certain special cases. Namely, you could occasionally use the law of sines or the law of cosines to do problems in 2D. But in general, if it's 3D, oh man, yeah, the standard method is, what would you do very first, Esteban? What's the very first thing you think I would want you to do?
So I started listing, so it's list VAE, and so it's 2 meters due east. So that's
Oh no,
straight in
now
the.
we're on the
Sorry,
next one.
wrong one. So
Yep.
A is 4 meters at 30 degrees north. So I would convert that to.
So no, okay, so it's not that what you're doing is wrong, but that's not what I would want you to do first. What would I want you to do before you do that?
Probably list VAE and then list VBE and then figure out VAB
Nope.
plus.
It starts
No?
with D. It starts with D and ends with raw.
Oh, draw.
If you don't draw it, you might screw it up. Now, that doesn't mean what you're doing is incorrect, but in my experience, if you don't draw this stuff first, you dramatically increase your probability of screwing up a northeast kind of switch. You know what I'm saying?
Okay.
So that's what I think you should do first, everybody. So, all right, thanks for and everything else I think you were saying was totally right on. Drawing pictures on paper can make you code better, make you think better. So do that. All right. So I'm going to try and draw it, and then we can compare our drawings. And remember, at any time, you can ask memo questions. You can email them and say, oh, this is too hard for me. Can you help me? All right. So I think I've got it noted here. So this is how I interpreted those words. And let's see if you did something similar. So north of east, 30 degrees. That means start at east, then go north by 30 degrees. This one is start at south, or sorry, start at west because you're going south of west. So you start at west, then go 50 degrees. Now notice, I did try to do these approximately to scale. You don't have to be perfect, but this line is supposed to be about twice as long as that line. Might not be, but and 30 degrees should be less than 45. So the better you draw your figures approximately, you'll just get in the habit of doing it. So if you draw everything as a 45-degree angle, you're going to be really confused. If you try to draw the angles approximately right, you'll do better. So this one is about 45 degrees. So I took 45 degrees and tried to draw it just slightly lower. Now, watch out. In this problem, we were not given the velocity of B relative to E. We were actually given the velocity of B relative to A. All right. So in this case, I'm going to now write out all my crap. So in this case, VBA is going to be, it looks like this angle is 50. So this side should be 8 cos 50. And it's going to be negative, right? Because going left. So negative 8. And again, I'm being lazy with sig figs just because I don't have room. All right. And then that's in the I hat. And then minus 8 sine 50 in the J hat. And that's all meters per second. Now, at this point, something you've probably noticed is with these types of problems, if you start out with meters per second, you always end up with meters per second. So a lot of times what I do is I get really lazy and don't even write the units. That's fine as long as you remember to put them on your final answer. If you forget on a paper and pencil test, you will lose points for forgetting units. That's a big deal to me. Okay. So let's just keep them in there for right now. So sometimes in the solutions, when I was in a hurry, I left the units off just so I could get through the math faster. All right. In this case, that's going to equal and there I got to leave off the units, or maybe I could just write them like this. Sorry, that's so squeezed in there. So 4 cosine 30 in the I hat, and I left off the degree symbol. I was just running out of room, that's all. So that's supposed to be meters per second on the end of that. Now, the next step is I need to write some kind of formula. I don't care which one it is, so I'm just going to start with something simple. What are we looking for in this problem? What are we trying to find?
I'm going to guess VBE is what we're trying
I
to
think
find.
so, yeah. It says, yeah, look, read the question. It says B relative to the Earth. So if I'm looking for VB relative to the Earth, I'm going to write a squeeze out there and related to that. So I know I need something with a B in it. So let's chart with this. I have VBA, so why don't I just start there? What is the other one going to have to be then? Well, I need to end up with Earth. So Earth has to go as the second subscript. There we go. And so at this point, it's vector addition. I know the vectors. I plug them in. I guess one thing in general that you have to watch out for is what if you end up with a minus with negative vectors? Then you got to remember you got a minus of a negative, and you got to think that through. All right. So, yeah. So, but that said, at this point, the rest is standard math. So let's go in and take a look at it. Where was it? It was right here. Give me a sec. So in this case, now this is the one that I accidentally screwed up the color code in the book compared to what I'm drawing on the board. So watch out if you're watching this video right now. right? Notice I accidentally called B the red one here and A the blue one for some reason. I don't know. It was just what I wrote at the time. So I should probably fix that up. Just because I think B means blue usually, and I don't know why I thought red for some reason on that problem. But yeah, so look out. You can see the picture here. And so notice I wrote, look at this. This is kind of interesting right here. I wrote a different equation at first. I said, give me BA is E. And then what I did is this is the one that we just wrote on the board. This was a different one that came to my mind when I was writing the solutions. And I still got the same answer. The idea was I said, okay, well, if that's true, then this is true. Then this is true. And then I just rearranged the equation and flipped this. So you get the same equation in a number of ways. So this part right here is that part right there. This part right here is that part right there. So there's the numbers. Notice you get a negative and you get this. Oops, you get this for the final answer in this case. The result ends up being this. So I'll pause for a second and see if that seems plausible to you, or wait for questions or any questions on this one.
So when I did it, I got VBE equals BAE minus VAB, but I don't know if that's right.
Wait, let me write it down so I can see. Say it again slowly. You said VBE
equals VAE minus VAB.
Okay, give me a second. So you said this, right? Let's check. VAE should be positive. And look, if you flip the order there, shouldn't that also be true?
Yeah.
So that's a valid way to do it. So that, yeah, and we can see that there's basically 2 ways to write this, 2 ways to write that. So there's 4 correct different ways to write this vector. And so, yeah, rather than trying to memorize your way out of it, I memorized that squeeze out trick and then just keep flipping signs until it matches the numbers that I have. Cool?
Can you go over that squeeze out trick one more time?
Yeah, again, so notice right here, A is the variable in the middle, right? So I know from experience, if A is the variable in the middle, it gets squeezed out and it doesn't appear on the left side. Does that make sense?
So, okay, yeah.
So B relative to A, then A relative to E. Well, the AA gets dropped out. And so this is what it looks like. If you have the A in the middle, you get a plus sign. And notice here, if you have the same symbol up front, you end up with a minus sign on one of the terms, but it's not always the same. So that's why I like this way better. Everything's always positive.
As long as the variable that's getting taken out is in the middle, it's always going to be positive?
Yep.
Okay, cool.
And that's easier for me to remember. And that, right? Because it's like, I don't want to have to keep track of all these signs. Everything's always positive when I write this down. And then I figure out the minus signs after that. All right. So let's go see. So in this case, let's see if you can understand this right now. So let me go to the solution really quick. And I'm going to make this a little bit bigger and scoot it over and down. There we go. And maybe I'll scoot back over just a little bit. Okay, so I've got all these on the screen, and I wanted to talk a little bit right now about this crap right here. What am I doing? What I'm saying here is this. Look at this equation right here. I am saying that BE, this term right here, VBE, that's this vector right here, is equal to the sum of the other two. Because I took the time to draw these arrows to scale, graphical vector addition should work as well. This is the first tail, the tail of the red vector. Notice I put the tail of the blue vector at the tip of the red vector. Said another way, the tail of the second vector is at the tip of the first vector. Finally, notice the result goes from the first tail to the last tip. And so that is graphical vector addition. So by drawing these approximately to scale, you should be able to check your math with a picture. And I'm telling you right now, the more pictures you have, the better. So if you wanted to understand this thing with the simulation, we could go and we could figure out these numbers in the code. But it might help to know, if we're doing code, what angle should I use in a computer code? I think this is 112.1 degrees negative, right? Because it's going from here all the way to there. I think I'm going to do a quick, I don't want to trust my math in my head. I'm going to do subtract 180 minus 67.9, 112.1. So here's how you could analyze this one in your simulation. Or I don't know, any questions before I go to the simulation? Let's go take a look. Oops. So now what I need to do, B was going to be, shoot, what was that number? 4.46. So let me get to my code and write this on here. It was 4.46, and it was at negative 112.1, I think, is what we just said. So check this out. If I wanted to do this, I could actually go into here and say this is 4.46 times the cosine of radians of negative 112.1. That's that one. I'll just put some space in so you can see it. So this just converts the thing to radians so that the computer knows what to do. This gets the cosine, and because I used a negative angle, this computer will get the negative result, because negative cosine of a negative 112 should turn out to be negative in your calculator. And so then for the y component, we'd say this should be a sine of that. And so now, if we want to understand this thing, we're ready to go. Let's see. We're supposed to get the motion of this relative to the Earth. Let's see if this seems reasonable. So there they go. And notice below here, we got some speeds. So there's that. All right, let's go back and run this again. And to check this, why don't we get the motion relative to A, and I'll explain why. So let's comment this out and look at the motion relative to A. And so now think, what should be the speed of B relative to A? The computer is going to spit this out for us. What should be the speed of B relative to A if we did our work correctly?
The opposite of VAB.
What did the problem statement say it should be? This was a number given in the problem statement.
Oh, it's the it's the 8 meters per second directed at 50 degrees. Or is it the first one? It's the one where
it's 8. So let's see. Speed of B relative to A is 5 point something. We better check. So something's messed up in this calculation. I wonder if something's wrong here. I'll take a look at this later and see if I can figure it out and send you an email, because it may be in my code actually. So I'm pretty confident that we did the math right there, but I will double check that. Oh, shoot. You know what I forgot? I didn't plug in A's velocity correctly. Do you see that? A isn't moving at 2, is it? A is supposed to be moving at what? 4 star cosine of radians. You know what I'm saying, everybody? Sorry about that. So now it should work out if we actually get the velocity of A plugged in correctly. Notice it's usually operator error. So in this case, now we should get 8. Forgot a parenthesis. Right there. And right here. So if you look, cosine is a function. The argument of that goes in the parentheses. Radians is another function. So yeah, now it should work. I'll just put that in there so people can see that a little better. Sorry about that. And, you know, I'm not trying to waste your time. I hope this is helping you visualize these. And notice here's that 8 number that we expect. So notice, what should you do all the time? Check your work as many ways as you can. All right, so that's the simulation. If you want to see it in slow-mo, we can slow it down here. Make this 0.5 so it goes a little slower. There it goes. Very cool. Notice they're almost moving straight away from each other. 4 and 4.6 at that angle, it's approximately 8. It's approximately 8.6. It's almost moving straight away. All right, let's stop for a second. I don't know if I'm helping or hurting you guys at this point with that simulation. What did you guys think? Did the simulation help you, or was it a waste of your time? Just so I know for future years.
I think it helps.
Okay. Anybody else? Esteban's been speaking up a lot today. Any other thoughts? Okay. All right. And I know ERT sucks a little bit. I'm just trying to do what I can. All right. Right on. Let me give you a different simulation that I didn't write. Let me see. How about this one? So let's think about this. So let me, oh, whoops, I forgot the screen share. Boo. Yeah, exactly. I need to add the arrows. I realized that after I wrote it. I think you're right, Jose G. We think the same way. Good job. That's a little scary though, huh? Now you have to know that you think the same way as a physicist. Ah! Oh yeah, that's a good idea. Maybe have it flash or something, or yeah. That's good. Some good thoughts, all of you. That's really good stuff. All right. All right, so now let's look at this one. The idea is this. Imagine you go to the airport and there's going to be a moving walkway. So this little gray strip right here, that is a moving walkway, an escalator at the airport or whatever. And so it's going to be moving this red person this way. All right. Now, whoops. In addition, there's going to be a person that's not on the walkway. And the idea is they're both going to run out and come back. Who do you think is going to win the race? They're both running at 5 meters per second. I don't know if you can see this. They're running at 5 meters per second each. Whoops, let me do that in red. So Mia is at 5 and Brandy is at 5. And the walkway is going at 2. Who do you think will win here? I'll see in the chat. Let's find out. So Jacob's got a hypothesis there, or a guess, I should say. He's thinking that red will win going to the right. Absolutely. And he thinks blue will take over. So let's find out. Here it goes. Where's the button to play it?
They'll probably just end up in the same spot and then I'll be back.
Well, let's find out. So on the way there, red's going 7. On the way back, red is only going speed 3. Blue overtakes red. Kind of counterintuitive, right? So you might think they end up at the same. Right at this instant, I have a question for you, a review question here. What is the average velocity of the blue? What is the average velocity of the blue? I'll check the chat here. What do you think? Exactly. Nice, Jose. Because remember, velocity is displacement with a P, not distance. Right? The total displacement is 0 in the I hat over how many seconds? 32 seconds. Okay. 32 seconds. All right. Now, in this case, what is the average velocity of the red? What is the displacement of the red? $18. And so I'm just going to punch in the numbers so we have that. It's about a half, right? So about 0.56. Doesn't matter on. Oh, go ahead. Sorry.
Just 18 meters, right?
It is 18 meters. Sorry about that. Yep, you're right. 18 meters. So this is 0.56 meters per second. So sorry about that in the I hat, because this was 18 meters, not meters per second right here. All right. So how do you get the average speed? What's V average?
Total distance divided by time.
Yeah. So what's the total distance in this case?
So for blue, it would be 200 meters. And then,
Careful, it only went to the end of the walkway and back.
160 meters. And then
160 meters over 32.
Red.
For red, what is it?
It's a little pat. Okay, so it's 80 plus 52.
Something like that. Yeah, exactly. Or I was going to say 160 minus 18. Agreed? So he does all of it except for 18. So I'll punch that in really quick just so we make sure that I think you said it right too. There's just two different ways. So minus 18 is, or 18.14. So 141.86. Which is about 52, I think, or something like that. So over 32 seconds. So just to point out, which one has the larger average speed? The blue one. Now, I have a funny version. Okay. So I'll get the numbers so it's all on the screen just for the heck of it and just for completeness. Okay. So the average speed of the blue one is exactly 5 because there was no moving walkway. On the way there, on the way to the right, it was moving at 5 meters per second. On the way back, it's moving at 5. We expect it should be 5 meters per second. The other one actually ends up slower, 141.86 divided by 32 is 4.43. Oh, whoops. So actually, the walkway doesn't end up helping you in the long run. It does help if you don't try to run backwards on it. Okay, so now let me just clean this up a little bit here. All right, and so I'll put a red dot next to this one. Whoops. Just so you've got it. This is the red numbers. This is going to be the blue numbers down here. And so just so you can keep track, all right? I'll get rid of those. I can't see the numbers. So now what I want to do is I actually want to look at the velocity versus time. Oh, and let me get rid of that arrow. Sorry, one more arrow to get rid of. All right. So let's go ahead and run this while looking at the velocity versus time plot. And so try to imagine what it should look like, and we're going to hit play. Red's winning. Red has a higher velocity going there. When they turn around, think what should happen. The velocity goes negative. We're not talking speed now. And so notice the blue one has +5 and -5, whereas the other one ends up being 7 and 3. And so at that lower speed, it takes longer for red to get back than the gain time going there. I like to do one more example of this just to beat this to death. All right, let's do one more example of this, and let me clear all my annotations first. What's going to happen? Oh, go ahead.
If we shorten the walkway, there'll be a point where they do meet up at the same time, huh?
No matter what length, that should always lose. The person on the walkway should always lose. So think about it like this: you have to cover the same amount of distance. But so if you cover let me show you this next example to show you why this makes, let me go like this. Let's say the walkway is moving 5 meters per second. Predict what should happen. I'm going to hit play. What's going to happen to the red one when the red one gets to the end and turns around? This race could go on forever. Red would never get there. Blue will always win, right? Now, remember, we're looking at a velocity versus time plot. If you want to see the position versus time plot, here we go. Red gets out there really fast, but now when red turns around, it's impossible for red to get back. Red stays at 80 meters forever while blue can go back and forth. And the idea is, this is an absurd limit, right? But any velocity greater than 0, let's try this down here at 1, right? So let's try the same thing again and run it. And the idea is red saves a tiny bit of time going out, but adds a significant amount of time going back. Ooh, that's going to be close, but blue still beats it. Got it? So now, obviously, the greater the velocity we see, the more absurd the outcome is. Is that good, everybody, on that? I think that kind of beats that to death. So that's kind of some physical intuition. Let me show you the problem in the workbook that matches that crap. So now I did a variation on this with a boat, 10 meters per second, and it goes up and downstream. And so what you could do is you could see if those things make sense. So that's a simple enough problem because there's basically only I hats plus or minus. I want you to do that one. Now I want to find out, oh, things are a little bit trickier. Let's see how you do it this one, okay? You have a boat in a river, and now notice I don't give you everything in a relative velocity problem on a test level question. You're supposed to figure out what is relative, what are the subscripts, what's moving. It's on you to figure that out. This is what makes these so hard for students. You're supposed to figure these things out from the words. Give that a shot. I'll write down what I think, and I'll give you a second to think about it, okay? So think about this problem, and in a minute, I'm going to ask you any ideas. So just think. And remember, at any time, if this is starting to get crazy, chat with Memo if you don't want to talk to me or... So I was just writing down the problem, getting it on the whiteboard here so you guys could tell me what to do. Esteban's been speaking up a lot. I appreciate it. And I know it's confusing. So remember, at any point, feel free to chime in, and it's okay to make mistakes because it's tricky sometimes. And sometimes you don't really learn it as well by staying silent. Sometimes making the mistakes makes you learn this a little bit better, okay? So it's okay to get it wrong in class. I expect that. I'm trying to trick you sometimes so you learn something. All right. Hopefully that's a good strategy. I don't know, but whatever. 4.30. That's what we're working on right now, right? All right. So this is the wording of the problem. The boat is going to aim some way here, right? You have to aim into the current somehow because the current's going to make you drift downstream. So we've got to aim upstream a little bit, and we want the boat to go straight up. I don't know. I want to know which way to aim the boat. I think in the picture, didn't they say it was looking for this angle right in here, theta? Which way are we going to aim? So obviously, if you go straight, if you try to go straight, isn't the river going to carry you downstream? So we can't just aim straight. We got to aim at some angle into the current. What is the procedure to do it? And some of you might just be able to solve this in your head intuitively, but let's try and write down some stuff in the same notation we've been using all day. I'll explain why after. Any guesses?
So the velocity of the river relative to the Earth would be 2 in the I hat.
Nice. And are you okay if I just say the velocity of the water relative to the Earth?
Yeah, sure. Yeah.
And how about we just say 2 meters per second I hat? Beautiful. That's awesome. So you could say a river relative to Earth, but I'm just going to use water just because I had this word water already written up here. That's all. Okay, yeah, next. Okay. Any other thoughts?
And so we want to find the velocity of the boat relative to the river or to the water, right?
Okay. I'm going to point out something here. In the problem statement, there was a sentence that had boat and water and speed all together. What do you think I gave you there? Now that I pointed that out.
Okay. So we have that.
We have what?
So
velocity of what velocity is that?
The velocity of the boat relative to the water is 10 meters per second in the J hat.
Nope.
No.
That's the velocity. So in the water, if there's no current, that would be. So we have to be careful. This is actually this number. That tells me the speed of the boat relative to the water. That is 10 meters per second, right?
Okay.
Now, think about this. Think about this. If there was no current, you'd aim this way and you'd get across at 10. Because we have to angle into it, shouldn't you get across a little bit slower? Because you have to use some of your energy to fight that current. You're going to aim this way and fight that current the whole way. And so as a result, you should actually get across the river at a rate less than 10 because you have to fight that current. So it makes sense that this side of the triangle, which is going to end up being the hypotenuse, is the bigger number 10. So yeah, and that's what I wanted to point out. Thank you for participating in that and struggling with that. So this is actually velocity of the boat relative to the water. Think about this another way. Imagine if you were in the boat and you throw a little buoy overboard right when you leave. The buoy would keep floating that way, and you would be going this way relative to the buoy. So I guess I could say it like this. This is kind of hard to do, right? But so let's say this is the boat, right? And you throw in the buoy. The buoy would go this way. You'd be aimed upstream, but you'd keep drifting like that. So again, the water's flowing that way. You're going straight up, but you're aiming this way. That is why this is the velocity. And so again, you could think of the buoy as being at rest relative to the water. So as the buoy goes that way, you are actually moving upstream relative to the buoy. Did that kind of help? Was that Jake?
Yeah, helped a little bit. Yeah.
Yeah, it's tricky. All right, so now let's see if we could write this. So I deliberately wrote this in green to try and not give it away, because that's the part that's hard for students. So that's what you got to struggle with in this one. So still water, boat, speed, that's what makes me think boat relative to the water. Think about this. What is the red arrow then? What's the last velocity vector?
That should be the velocity of
That's the velocity
the boat relative to the water. No, the boat relative to the earth.
Yes, and that is our goal. If you're standing on the shore here, you want to get straight over to the other side. You want to move straight up relative to the earth. And now at this point, it's easy, sort of. Okay, so let me just write this out really quick. Velocity of the boat relative to the earth. I'm just going to write any old squeeze out that fits. So that's going to be a boat water. And then we got the water relative to the earth. Is that going to give me the correct squeeze out? Let me verify. I see that, aha, this has boat and earth. W should get squeezed out. It does. Feeling good. So now that I know that, I'm like, this is a legitimate equation. I could write these out. Now, you could try and draw this as a triangle. I want to show you that some of you might see, well, wait, shouldn't it just be this? Can't I just say, well, shit, man, this is 10, and I know that this is 2, and shouldn't I just end up going straight up? You could do that. But I want to show you this works in this special case because everything's a right triangle. So you could use this, and notice you get sine inverse of some angle is 2/10, right? So here's the angle theta. Opposite over hypotenuse is sine theta equals 2/10. Now, I want to do this with the vector work because that works every time, even if you have 3 dimensions, etc. So what I'm going to do is I'm going to say this. This equation is actually 3 equations. It's 1 equation in the x direction, 1 equation in the y direction. And so to speed this up, I'm going to go to the solutions just because we're running out of time. I just want to show you the solutions here. Sorry, my markers are falling down here. Okay. You know what? Maybe. So what I did is, again, I tried to draw this. This was the horizontal equation that we just wrote up. And this was the vertical equation from what we just wrote up. Maybe I should do one more line on the board. I apologize. Sorry about that. Let's do one more line on the board before we go to that. So the idea here is, take a look. I see VB Earth in the X direction should equal velocity of the boat relative to the water in the X direction plus velocity of the water relative to the earth in the X direction. In this case, the water earth X is this number 2, and it's positive, right? Because it's all in the I hat. So this number down here should be 2. I'm leaving off the units just because I'm running out of room, et cetera, et cetera. This might help. What is velocity of the boat relative to the water in the X direction? Somebody try. Anybody?
-2.
That's true. How do you know that?
Because of the triangle.
True. So what are you saying this has to be?
0.
Yeah. Now look at this. So let's go that way. So Esteban's doing a lot of work in his head correctly, which is awesome. But think about this. If the boat travels straight up, how much does it go in the X? None. It's all in the y. That was the point. So what he's saying is, well, shit, shouldn't this be -2? Absolutely. But I want an equation for that in terms of theta, because just saying it's -2 doesn't help answer the question. Remember, the question asked, oh, question, where are you? The question says, what angle should you aim? So let's go back and look at that. Is there a way you can get the angle involved in that, Esteban?
It would be sine theta. So negative sine theta would give you the x coordinate.
Negative 10
Yeah, 10
sine theta, right? So again, if it's going up and to the left, in this case, sine is opposite, negative because of the negative arrowhead. So that means we could go down to here and say this is -10 sine theta. And from there, notice we could rearrange this and you get exactly the same result. 10 sine theta equals 2. And theta equals sine inverse of 2/10. Now, I was sloppy with the units here, but do notice this. Whoops, sorry. Do notice that this is 2 meters per second, 10 meters per second. And so the meters per second end up canceling out in this special case. So I wasn't trying to hide anything there. So go into that solution now. I know it's almost time to go. Let's see if there was anything else in there. So, oh, there's the answer, right? 2/10 is 1/5 is 11.4. So, and notice from this, you can get this. So I'm going to let you finish this one out at home. All right. And I think you could see how it's not the math that's going to get you on this. We've been doing vectors till you're blue in the face here, but you do need to put some energy into these problems. Turns out, I think we have all next week, to keep doing more practice on these problems. So this weekend, a great thing to do would be to do extra problems and find out what you don't know. It could be those 2D projectiles. It could be standard. It could be non-standard. You could take this time to take some practice tests and see how crappy you are when you get a real test. And so if you don't know where those are, I'll show you that. I'll show you that right now. What the heck? Let's just do it. So give me a second. Zoom's got so many things here. So if you go to here, if you want to do some practice tests and find out how you're doing overall in the course, this might be a good weekend to do that. If you want to get caught up on your other classes, if you want to leave right now, whatever you want. But so again, what am I doing? I'm clicking this link right here, Phys 110. And then I've got all my old exams and I've got the solutions. So here's the chapter 1 and 3 stuff. Here's the chapter 2 and 4 stuff. So because we've pretty much done all of chapter 4 now, we're just going to do extra practice on it. You could, in theory, try all of these old tests and see how good you are. If you're going to try the test, this is what I ask that you do. Give yourself 80 minutes exactly. Pretend it's a timed test so you could practice as if it's a real test. Also, don't look at the solutions at all during that test time. That way you get used to the pain of not knowing everything right away. People that use the solutions all the time fail real exams because they don't know how to deal with the stress of not having solutions in front of you all the time. So if you want to get it, and we'll do this next week, I'll mention this again. I'm going to stop the live stream now. Oh, shoot. Where is my Zoom? Where's my Zoom? Let's get back to it. There we go. And I'll check the chat in just a second here.